Hi, and welcome to 1.3 Adding Vectors. So for this lesson, students will be able to define and give examples of scalars, define and give examples of vectors, and not only that, but they'll be able to add vectors algebraically, so like mathematically add vectors together. Scalars. The definition of a scalar, not scholar or anything, scalar, quantities that are fully described by a magnitude, size, or amount. This term magnitude is going to come up again and again and again. There'll be questions like calculate the magnitude of the acceleration. In that question, they're asking for the size of the acceleration. How many meters per second squared? All right, like maybe it's 5 meters per second squared. Or is it 6? That's the magnitude. What is the number? You could have the magnitude of the acceleration, magnitude of the velocity, magnitude of the force. It's just asking, that's another word for size. All right, it's going to come up again. I'm telling you, you might be confused. You might forget. All right, so that's a scalar. All you need is the size. For example, Chris is 70 kilograms. Bill walked 7 meters. Jan drove at 25 kilometers per hour. Steve has $5. It took 7 minutes and 42 seconds to do the homework. These are all amounts. What's missing from these, you might be like, okay, whatever, so I really don't get what a scalar is. They are not specified by a direction. So it doesn't matter how far, what direction Bill walked in. All we care about is how far he went. He went 7 meters. That's enough to describe a scalar. If he goes 7 meters north or 7 meters east, you're describing that quantity a little bit differently. And then it doesn't become a scalar anymore. If you give a direction, it becomes a vector. And that's the difference. And you treat scalars and vectors differently. So scalars are only the size. Like Steve has $5. You wouldn't say $5 up or down. You wouldn't give a direction. It's just the magnitude, how much of the thing. And you've added scalars your whole life, or at least since kindergarten. Steve has $5, Jan has $3. How much do they have together? $8. Bill walked 7 meters and then walked 3 meters. How far did Bill walk? 10 meters. The story ends there. When you're adding vectors together, it's a little bit differently because you have to take into account their direction. So how would you add directions together? Let's see. Well, here's the definition of a vector. And by the way, you could be writing these down in your notebooks, right? So I'll have throughout the year slides like this one where it has the definition. And anytime you see a definition, examples, formulas, you can write that in your notebook. Anyway, vectors, quantities that are fully described by both a magnitude and a direction. So you need both to be considered a vector. All right, and examples would be Bill walked 7 meters east. As soon as you tell me the direction, you're thinking it's a vector quantity. Okay, so vectors are represented by arrows, and arrows are super cool because they have a length. That's the magnitude. They also have a direction. So it's a size, but it's also a direction, and that's why arrows are the perfect way to represent vectors. Jan drove 25 kilometers per hour northwest. You could also represent that velocity with an arrow because it's a vector quantity. It has a magnitude and it has a direction. And when we graphically add vectors, you could make these arrows to scale with like a ruler, and then you could use a ruler and a protractor to add the vectors together. That's graphically adding vectors. Today we're going to add these vectors differently, I think. Oh, and then, oh, look at this. A former student said, oh, that V looks like an arrow, and arrows are vectors. So if that helps you remember, vector is an arrow. It needs a direction. That's a cool way to remember that too. Critical thinking. Can we add vectors the same way that we add scalars? It was easy to add the scalars. No! I didn't give you time to critically think because I kind of gave you. So this is how you algebraically add vectors together. The sum of two vectors is called the resultant vector. So one vector plus one vector, and then you get a result, or a resultant vector. And keep in mind, vectors are always added head to tail, okay? Keep that in mind, head to tail. But what does that mean? So we have two vectors here. We want to add them together. First, we have to identify which side is the head and which side is the tail. So take a guess which side is going to be the head of this particular vector. Which one would you consider the head? Is it this one or this one? Okay, the head of the arrow is like that. It's like an arrowhead. That means the other side is the tail. And same with this one. So you have to connect them head to tail. Never head to head and never tail to tail when you're setting up the vectors to add together. So it should look something like this. Okay, we have a vector that goes west and a vector that goes north. Now, when we're determining the resultant doesn't go head to tail. You might think, oh, let me make the resultant. So that means I have an arrow going this way. Head to tail, I'm good. No, no, no. When you draw the resultant vector, it has to be from start to finish. So the problem with this is we have a vector going west and a vector going north, but look at our resultant vector. It's going down and to the right. It's going southeast. How could a west and a north make a southeast? That's the total opposite direction. So instead of continuing with our head to tail mantra, when you're drawing the resultant vector, it's always from where you started. Picture yourself like a little person on the screen, and you're going to walk up, and then you're going to walk over, and you finish here. So from start to finish, just like that, that's the resultant vector. Okay? So the resultant vector head does touch the head of one of the original vectors. That's okay. The whole head to tail mantra is just when you're setting them up. If you want to add two vectors together, those two vectors have to be set up head to tail. When you're ready to draw your resultant, you draw it from start to finish. Okay, because you want north-west, and this is going northwest. The resultant is drawn from start to finish, so you could add that to your notes if you would like. So it says find the resultant of the following vectors: north with a magnitude of 7 and east with a magnitude of 4. So let's start by drawing a picture. A good place to start in physics is to always draw a picture. Okay, so north is just like this. North is going up. We know that, right? What direction is east? Is that going to be left or right? Well, if you remember what the compass rose looks like, okay, by convention on our piece of paper, we'll always make north up unless told otherwise. That means south is down. And what direction is west and east? Just remember the word we. Okay, that means west is left on our paper and east is right. So since it's east with a magnitude of 4, we will draw a vector going east. But the question is it better to write, is this option A, or should we draw it like this, option B? Which one would be better? Option B is better. Why? How are these two connected right now? Tail to tail. Option B is better because the head of the 7 is connected to the tail of the 4. Okay, so now that we know we're going north and east like that, I could draw in the resultant vector, and you'll see this vector from start to finish goes northeast. So our goal is to figure out, okay, that's the resultant. What is the magnitude or the size of the resultant? And what is the direction? The way we'll do that is with our good old pal trigonometry. Did you notice that I drew a right triangle here? So now that we know the two sides of the triangle, we can find the hypotenuse. The resultant is the hypotenuse. So how long is the hypotenuse? So we have the two sides. We're going to use Pythagorean theorem to find this length. We'll write the formula down, then plug in the numbers, and we'll get a value of 8.06, or we'll round it to 8.1. So the magnitude of the resultant is 8.1 units. We don't know if it's meters or meters per second or even newtons yet, so we'll call it units. Don't forget to write your units. So that's the magnitude, but how do we determine the direction? Can we just say, okay, northeast? That's not as specific as we can get. We could do better, all right? Not just northeast. let me put it this way. How much north are you going? Are you going just a little bit north of east and this angle is super small? Are you going maybe exactly 45 degrees north of east? Or are you going mostly north? Then you're going a larger degree north of the eastern direction. You could also say in the future, you could go north of west. So is it a little bit north from west? Is it more? How many degrees north of west? The order that you say matters, because we could even say how many degrees, this one, how many degrees west of north? Okay? You could either say north of west or west of north. You could say north of east, that's this many degrees north of east, or what is this angle? How many degrees east of the northern direction? It gets a little bit confusing, but the way you say it does matter and it'll help describe the angle. So for now, we'll find this angle, and that'll tell us how many degrees east of north we're going. So to find that angle, now that we have three sides, we could use any of the trig identities, but since we rounded this one, I like to use the unrounded ones. So we have opposite and adjacent. And if we have opposite and adjacent, are we going to use sine, cosine, or tangent? We'll use tangent. So we always start by writing the equation, then we'll plug in what we know. And now we can solve by doing the inverse tangent. We're trying to get that variable, the theta, by itself. And you get an angle of 29.7 degrees. So we will say, oh, let me write it in red to be fancy. So we will say the resultant of those two vectors is 8.1 units, 29.7 degrees east from north, or east of north. And if we wanted to write it in one line, it would look something like that. 8.1 units, 29.7 degrees east of north. It's getting a little long here, but we'll try this one. It says find the resultant of the following vectors. West, so that means left, with a magnitude of 20. So we're going west, 20. And we're going south, 9. South, 9. So the resultant should go to the west and down south. What is the magnitude? What is the direction? We'll start by doing the Pythagorean theorem. Oh, well, you try it first. So pause the video and then I'll go over it quickly here. Try it first. Pause the video. Okay, now hopefully you did the Pythagorean theorem, plugged in the numbers, and you got a magnitude of 21.9 units. And then to find the direction, if we're looking for this angle, you could do opposite and adjacent and do tangent again. Plug in your values. Do the inverse tangent, and you get an angle of 24.2 degrees. But how are you going to name that angle? That's the question. So I'll write it all out. The magnitude and direction of the resultant is 21.9 units, 24.2 degrees, and we're going this many degrees south of west. All right. West of south would be this way. If this is south, this many degrees west of the southern direction would be a different angle. So south of west is different from west of south. Oh, I have it right there. I forgot I put it there. Okay, so if you did the west of south, it's not wrong. Okay, if you got an answer of 65.8 degrees Just as long as you said west of south, you would be totally correct. You're just naming the angle differently, but it's still correct. All right, there's another practice problem here. It's already 15 minutes in. I guess I'll do this one quick. You could try it. It's tricky because you have to set up the vectors. North with a magnitude of 5, west with a magnitude of 3, so that's this way, and south with a magnitude of 4. So you had to do some critical thinking here. Get this out of the way. How would you find the resultant? The resultant is from start to finish, so we could do that same process, but I don't see a right triangle anymore. What would you do? Pause the video and think about it. Okay, hopefully you thought about it. You can make this a triangle, okay? And you could make that, all right? That's one way of thinking about it. There's other ways to think about it. But then you have to say to yourself, okay, I made a triangle. What are the lengths of those? So hopefully you can see that this is just 3. And then if I went up 5 and then down 4, how long is this leg of the triangle? That leg of the triangle is 5 minus 4 is just 1. It's like you're doing a vector addition head to tail. Here's one vector, and then, so that's 5. And then the 4 head to tail comes like this. And then the resultant, so this one's 4. The resultant is from start to finish. You can do this linearly, and then it's just 5 minus 4. I jump right into the trigonometry because, you know, the linear stuff, it kind of makes sense to me. Hopefully it makes sense to you too. So we jumped over that, but that's how that works. So now we have a triangle that has a length of 3 and 1, and you should be able to find the magnitude and the direction. And I'll write it out. This is the magnitude portion, 3.2 units, and I'll write the direction portion. We're going to use tangent again, and remember, this is the opposite and this one is the adjacent of our right triangle that we made. So that angle is 71.6 degrees, but I want you to think about it. Is that 71.6 degrees? What direction is this going? First of all, this is going west and it's going north. So is it 71.6 degrees north of west, or is it 71 degrees west of north? Think about it. The angle's here, so it's telling me I'm going this many degrees west from the northern direction. And if you found this angle instead, you would be going up. You would be going that many degrees north from west, and I think I have it written down here. Yeah, so it would only be 18.5 degrees north of west. Sorry that my animations kind of went over there. And then that's it. Thanks for watching. Have a good day.